In this video, we're going to be taking a look at 3.1, the derivative and the tangent line function. And we're going to get to what the tangent line is. So that's an example of the tangent line and how it ties into the whole idea of the derivative. So the big question we're trying to answer here is, how do I find the slope at a point? So we've never done that before. So you're finding the slope at a single point, because previously you've always needed 2 points to find the slope. And how is that tied to the idea of a tangent line? Okay, so in class we'll do the exploration together on 116. So let's take a look and just jump right into the definition of tangent line with slope m. So if you need some help, look at on page 117, look at that diagram, and that's fine. But so right here at the right, we have a point C. Okay, so this is the point C, and then your y value is f of c. Like this is x and f of x, but we're using c. And we want to find the slope at that point. Well, we can draw what's called the secant line. So this line right here, that I will highlight in red right there, that's called the secant line. And that's what we had done in Algebra 1. Now what we're doing is we're trying to draw the tangent line, which is a representation of the slope at that exact point, right? So it's going to look something more like this. If we draw the slope at that point, this is more along the lines of what the tangent line would look like. And that's kind of our goal, is how do we get the slope of that line? You can see that it's nowhere near what it is there. Nowhere near what the secant line is. So let's look at this picture. Let's look at this one that we have. So here is C, f of c. And we want to approximate that point. So what we're going to do is we're going to take another point up here. Okay, whereas we're going to say that this change right here, that is going to be, let me zoom in, that is going to be the change in x. Okay, and our goal, so then this is going to be c plus change in x, so c plus change in x, and then f of c plus change in x, whatever that change in. Now our goal is to get it so that change is incredibly small, right? So let's go ahead and draw another picture so that, okay, here we have, it's the same. There's c, f of c, and then let's choose a point right here. So now you can see this change in x right there. That's even smaller than the change in x up there. So we want that change in x to get incredibly smaller. In other words, we want that change in x to approach 0, right? So that's the big idea. We just spent a chapter on limits. So if we were to write this as limits and kind of what we want to happen, it would look like this, right? This limit as x, the change in x approaches 0, right? That's where we got this down here. We want that. And we want the slope, so we're doing the change in y over the change in x, right? Because that's the slope. We want as change in x approaches 0. Whoops, that's change in x on the bottom. But remember, we can't exactly plug 0 in there. So we're going to rewrite this in the context of more along the lines of what we're doing. So it's going to be the limit as the change in x approaches 0 of, and we're going to do y minus y still, right? Because you have y minus y. Okay, so let's do f of c plus change in x minus f of c all over. Then you'll have your x minus x, and that would be your c plus change in x minus c. I'm going to rewrite it again because you notice on the bottom those c's will actually cancel. So let's rewrite it one more time without those c's. So the limit as the change in x approaches 0 of f of c plus change in x minus f of c all over just the change in x, right? And that is our slope. Okay, so that's the definition of the tangent line. So right here, let me highlight it. I'll highlight this in green right here. So make sure that's in your notes. And this is the definition of the tangent line. Okay, the tangent line, that's like hive, tangent hive, but it's tangent line. There we go. Okay, get that down, and then let's look at an example. So first of all, it says find the slope of the function at the given point. Okay, and this, we know this is calculus because at the given point, so it's asking at a single point, whereas in algebra they're not asking between 2 points or even the slope of the line. This is at a given point. Now looking at this, you should know what the answer is. Thinking of algebra, look at your equation, y equals mx plus b. What is the m? That's your slope. So we know what the answer is. I'm not going to say it, but you all should know what the answer is, which is why we're going to use this definition that we just used up here to go ahead and use that definition to see if we get the right answer. All right, so I'll help you get it set up. It's going to be the limit as the change in x approaches 0 of, now it's going to be 2 and then x. Remember, that's where you're plugging in your c plus change in x. So we're plugging in the c plus change in x and then the c. And in this case, your c is 1 right there. Excuse me. So it's going to be 2 times, now it's going to be 1 plus change in x, 1 plus change in x. Okay, because you're plugging in, like I said, c plus change in x. And then in the second one, it's going to be minus 9 minus, I'm going to put parentheses because I'm subtracting all of that away again. It's going to be 2 times 1, or the c, which is my x value, minus 9. All over the change in x. Now, obviously, we can't take this, right? We can't take this and plug it in. So if we take 0 and plug it in, we'll get 0 in the denominator. We've already studied why we can't have that. So let's go ahead and simplify the top as far as we can. So you take it from here. You simplify the top and kind of see what happens as you work things through. Okay, now if you work it out, you multiply stuff in, like right here, when you take this 2 and multiply into those parentheses, you would end up with 2 plus change in x, and then you take that negative and distribute it into that 2 and negative 9. You get a negative 2 and a positive 9, which you can see a bunch of stuff cancels right here. All right, and so now, once things cancel, all you're left with is the 2 change in x on top and the change in x on the bottom. And you notice those will actually cancel, giving you just a constant. So the limit as the change in x approaches 0 is a constant, and we learn that the limit of a constant is that constant. So that is the slope at the point 1, negative 7. Okay, and so that would be our final answer right there. Now, that's all, like I pointed out at the beginning, hopefully you were able to figure out that 2 should have been our slope right away because it's in the m's position. It's a linear equation. But now, let's take a look at a non-linear equation like this quadratic. And we want to find the slope at the given point, which is 2, negative 5. So go ahead and use what we did back here. Use the definition and set it up and see if you can do this one on your own. Okay, so let's break this down step by step here. So the first thing I do is going to plug in. For x, I'm going to plug in my c plus change in x, which in this case c is 2. And then I'm going to do that. So you have the minus 9, so it's your function minus itself with just c in there. So I plug in c there, and then c plus change in x there. And on the top, I'm going to have to distribute this out. So right here, you have to, this is being squared, so you distribute it out. And you would get 4 plus 4 change in x plus change in x squared. And I put change in x in parentheses to show that it's all of that squared. Minus 9 minus 4 plus 9. Right? Then you look at things and see that they could cancel, like you have a positive 4, negative 4, negative 9, positive 9, and then you're just left with these two terms right there. And you notice that this one, and this one all have at least one change in x, leaving you with just a change in x right here. So then you're left with 4 plus change in x. Now when you plug that 0 in, you get 4 plus 0, which is just 4. And so our final answer is going to be the slope is 4 at 2, negative 5 on the line g of x is equal to x squared minus 9. So if you graph that thing and look at 2, negative 5, and draw a line with the slope of 4, it would be the perfect tangent line at that point. Now let's just take a look at the beauty of this and what we were able to do with the idea of calculus here. Now we're able to find the slope is 4, but let's go ahead and just show that what we did is correct. Go back to algebra and do this. What we're doing is we're finding the equation of the line when the slope is 4 and the point is at 2, 5, right? So you go y minus y is equal to m times x minus x. You get y is equal to 4x minus 13. So let's look at that on a graph. So here we have our point 2, negative 5, our equation x squared minus 9. Let's go ahead and get to graph that that line that we find. So that's the equation of the tangent line and the point. See how it perfectly goes through that point, and it is a representation of the slope at that point, which they have huge applications that we're going to learn later on as we study the idea of the derivative a little bit more. And now here, the vertical tangent line right here, that's if you do all of this and you still end up with something over the change in x, and there's nothing that you can do, that means there's the vertical tangent line, right? And that can occur with vertical asymptotes. There can even be a function like this that looks like this, and right in the middle it goes straight up and down, so that slope is a vertical tangent. So sometimes they can exist, just be on the lookout for them. They're kind of rare, but if all of this doesn't work out for you and you do the math correctly, then it means it's a vertical tangent line at that point. So we already wrote the definition of a derivative, but let's go ahead and write that again. And this time we will write it without the c's. So right here, this is really important. That f prime of x, that means the derivative of your function f. So that's shorthand in function notation showing the derivative, right? So please remember that. And anytime you see that, and you're going to see it quite a lot, f prime of x, that means the derivative. Okay, and so here is then our definition, and what we did this time is we replaced c, because c just represented a point on the graph, so it's less confusing, but here we threw in x, because it's your x value. At what x value you're finding the slope at that specific point. Okay? And we don't know the change in x, and in fact we want the change in x to approach 0, so we want it to be infinitely smaller. And it's really cool the fact that we can do this so easily with this derivative formula. Okay, then down here defining differentiation, differentiable on and over an interview. So differentiation, this is the act of, finding the derivative. Or differentiate, all of those are kind of what you're doing. That's the action of finding the derivative. Differentiable is kind of the whether or not a function, I almost said like being of the function, whether or not it's differentiable. And by it, can it have, I mean function, a derivative at that point. So can it have a derivative at some point xy, okay? And then differentiable on an open interval. So sometimes that's given to us, you know, either a to b, whatever that might be. It could be from -infinity to infinity. It just really depends. So you have to be careful. Sometimes you're asked specifically to look for intervals. And a few things just that I want you to be familiar with. Be familiar with the notations. Let me get a different color. Dy dx, that also means the derivative. Limit as change in x approaches 0 of change in x over to change in y. That also means a derivative. So this d right here, that just means delta. Because the triangle symbol, that's the symbol for delta. And in math, the delta symbol just represents change. All right, so delta y, delta x, that's change in y, change in x. And over here, which this will probably be one of the most common ones, that dy dx, that's delta y, delta x, right? I'm going to say that this is probably the most common amongst most textbooks. And also, this is another way to show the derivative that is in the form of the definition of the derivative. And the last way is what we just looked at above right here. This is in the form of a function. Okay, so those are all different ways to show the derivative depending on the context. Like I said, the most common one is that first one. If the second common one is probably going to be that one. Okay, so definitely know those two, but be familiar with all three. Let's go ahead and do another example. Finding the derivative by the limit process. So this is we're not given a point. This is finding the derivative equation. So meaning, if we go back to here, it would be finding an equation for this red line that of the derivative where I could plug it in. Like if I wanted to know the slope at this point here, right here, I could plug those values into my equation and know what the slope is. So if I have it here, I would want to know, I could know what the slope is. Right here, I could know what the slope is, but the slope is horizontal, right? Because it's a minimum point there, so it's going to be 0. But my equation will reflect that. So that's our goal with this next problem, is to go ahead and find that equation. It's the exact same, only you leave x as x and you don't plug a value in for x. Go ahead and try this one on your own, see how you do it, and then come back. All right, so there's a lot here. So if we start from the beginning, we set it up. This is the most important part, and probably the most difficult part when we're first starting this is setting it up. Inside, that's where you would have, inside your function right here, you would have the x plus change in x, and then your x over there, right? Everything else stays the same. Use parentheses. These parentheses are really important right here and right here, because on both of them you have that negative on the outside that you're going to have to take in, right? So be thorough and be clear when you set it up. Then we're going to have to go ahead and multiply this part out right here, and that's what all of this is. And now to see what things cancel, I went ahead and, I distributed this into all of those, right? And this is one term, 2x times change in x. And then when you distribute those in, you'll see that the negative x squared and the positive x squared will cancel, that 2 and the negative 2 will cancel, and you are left with only the negative 2x change in x minus the change in x squared. Now that's not x squared, that's the change in x squared, so all of it squared over the change in x. Because then over here, everything has at least one change in x, right? So this goes down to a 1 because you still have change in x to the first. So the limit as x person, now we can go ahead and plug this in, and that's where the negative 2x minus 0 will become. And then this right here is our final answer. This is the slope of the tangent line at any point on the graph of, what was it, 2 minus x squared. Now that's hugely applicable because if you know a certain particle is moving a certain way, and you can then find the equation for the derivative, you know how fast it's moving at any given point, right? Okay. So let's do another example using the derivative to find the slope at a point. So find the f prime, remember that's the derivative, for your function. So here's your function. Then find the equation of the tangent line. This is what we did, right? We're finding the equation for the tangent line. So once you figure out what the slope is at that point, then you'll have to go and figure out what is my y-intercept, or you can set it up into the equation like what we did up here, right there. So you're doing the same thing as we did there. All right, go ahead and try this on your own. Graph them on the same plane like what we did back here on Desmos, just to make sure that your answer is correct. Go ahead and try this on your own and then come back to the video to see how you did. All right, so let's see how we did here. This is another tricky one. So first of all, I just set up, so the derivative looks like this. I'm plugging it into this function, but I know what that x is, so I'm going to plug 1 in for there, and that's where that and that came from. And so f prime of 1 is what I want to find, the derivative at 1. Okay. Then we set that up, and you notice you can't plug 0 in, so you have to multiply by the conjugate. So I multiply by the square root of 1 plus change in x plus 1. Well, right here, this is just, you could change that to 1, that's fine, because that's 1 as well. But I multiply by the conjugate, and when you do that, and here's the reason we do that, it's because when you do that, when you multiply this and this together, you get 1 plus change in x, but then your middle terms will cancel because this plus this is positive, that plus that is negative, they will cancel. So really it's just your first terms and your last terms, and my last terms are negative 1 and 1, which is where that negative 1 came from right there. Okay, so this is what we have over here, but the 1 and negative 1 cancel. That's why these are marked out, and you have just the change in x, but you notice the numerator and denominator both have a change in x because this needed to be multiplied over there, and I just left it out there. Now, once everything cancels in here, if you need to pause it to kind of digest this a little bit, just go ahead and do that. But over here, when all of the smoke clears, this is what we have. You have a 1 in the numerator, and then the square root of 1 plus change of x plus 1 in the denominator, and you can plug it in. So right now, if you plug that in, you end up getting just 1 over 1 plus 1, which is 1/2. And so this is our slope at 1, 1. Okay, now what they wanted was the equation for, I believe, the tangent line, the equation of the tangent line. Now we have the slope and we have the point. So if we have the slope and the point, we can plug that in. So it's going to be y minus 1 is equal to the slope times x minus 1. And on a test, if I just ask for the slope of the tangent line and you stop there, that'd be great. You know why? Because that is an equation. Or sorry, if I ask for the equation of the slope for the tangent line, that would be the equation. You could be done there. Or you can solve it for y, which really isn't that difficult because it'd be minus 1/2 plus 1. So y is equal to 1/2 x plus 1/2. All right, so then that would be your equation for the tangent line, and you would graph both of those on the coordinate plane to make sure that your answer is correct. And we look at our graph. This is what we have. At the point 1, 1, the red is our graph, square root of x. You can see our equation of the tangent line, 1/2 x plus 1/2 matches perfectly. So hopefully you got the same result. All right, so looking at this, if a function is differentiable, okay, then that would imply that it's also continuous, okay? But if it's continuous, that does not imply that it's differentiable. It doesn't work the same way, right? So, for example, every function that is derivative, it has a derivative at every single point, is continuous. We know that has to be true, and we'll learn kind of through this chapter that that's true. However, if you take that argument and spin it, you look at a continuous function, it's not always differentiable because functions are not differentiable at these things called corners, or as we saw earlier, vertical tangents. And you're going to see corners at absolute value functions, and you would see something like vertical tangents, also asymptotes. So if you look at y equals 1 over x, right, that has those asymptotes. They are not continuous at those points. So you need to be careful. Also, piecewise, you need to make sure that your one-sided limits are equal to the value at that point, that those three things are equal, and then also make sure that it's not a corner. So we have to look at one other thing is, hey, are the slopes the same, either coming together and at that point? So not only are the y values, but are the slopes the same, right? Because if you think about a corner right here, the slopes of this line and the slopes of that line are not the same. But if it were smooth like this, the slopes of this line are, at this point, are the same as the slopes of this line approaching that point. Okay, so that's why you cannot have a derivative at a corner, because the slopes are not approaching the same value, just like you couldn't have a limit if the y values are not approaching the same value. Okay, so let's take a look at this one. So graph the function f of x is equal to the absolute value of x minus 2, and g of x is equal to x to the 1/3, and identify the points where the graph would not be differentiable. Go ahead and do that, and come back to the video. If we look at the function, the absolute value of x minus 2, you notice right here at this point, right here where the left side and the right side come together, that is where it would not be differentiable. At this point, at 2, 0, there we go. At that point, it would not be differentiable because it is a corner. And then if we look at the next one, this one would not be differentiable right here at 0, 0, because it has a vertical tangent at that exact point. So if we were to do the definition of derivative for x to the 1/3 at 0, it would not exist, right? Because you would have 0 in the denominator. But if we did it at 0.00001, then it would. But at 0, it would not be differentiable. All right, and this is what I mentioned earlier. If a function is differentiable at a point, then it implies its own continuity, right? So for example, if you look at the graph of a rotating tire, right? If the look at the rotating tire. So here's our tire, and imagine there is a piece of gum stuck to this tire, and that piece of gum travels around, right? When that piece of gum hits the ground, what happens? Well, it switches directions and goes up. And then that piece of gum comes back down because you still have the same tire over here. So this is tire. Oops. The gum is still right here. So then the gum goes back down and then comes back up. So your graph is going to look something like this. Now, here's the thing that is going to blow your mind. That piece of gum stops at these points. That piece of gum is not moving at those points. Okay? Which is why if we try to find the derivative at those points, it's going to be non-existent. Because when you're looking at a graph of position or of the movement of an object, the derivative represents its speed, right? Just like when we thought about speed over time. So the speed, if we know the position, how fast it's going over time, then we can determine how far it's gone, right? But these are position, like where is it at in any given time. And so the slopes of this green graph determine how fast it's moving. And so at these points, it's not moving at all. All right, so I know it's tricky, but that's a reason why even though it's continuous, it's not always differentiable, but if it's differentiable, it's always continuous. All right, so that is it for 3.1, the derivative in tangent line.